Ever wonder if you could reliably predict next quarter sales? Or maybe know exactly how much energy a city is going to need next Tuesday? It sounds a lot like magic, but it's not. It's a really rigorous discipline called time series forecasting. And today, we're not just going to skim the surface, we're giving you the architect's blueprint for building a forecast that actually works. Okay, let's dive right in.
Really, it all comes down to this one single huge question. How do we teach a machine to look at what's already happened and then make a smart, reliable guess about what's coming next? It seems pretty straightforward on the surface, right? But the entire process is governed by one simple, unbreakable rule that changes absolutely everything.
And this is it. This is the one unchangeable law of all temporal analytics. Time only moves in one direction. Now, I know what you're thinking. That sounds ridiculously obvious. Kind of like saying water is wet. But you'd be shocked how easy it is to actually break this rule in the world of data and algorithms. Every single choice we make, from prepping our data to testing our models, has to respect this principle. If you mess this up, your forecast isn't just a little off. It's a complete illusion.
So here's our blueprint for building a solid forecast. First, we're going to really nail down why time is just fundamentally different. Then, we'll get into the fun part, the alchemy of teaching a machine to read a calendar. After that, we'll look at the different engines you can use to actually power your forecast before we expose the one single cardinal sin that can make the whole thing just crash and burn. And then, we'll wrap it all.
So let's start with that foundational idea. See, in most machine learning problems, you could take a spreadsheet of customer data, shuffle the rows all around, and you wouldn't lose a thing. But with time series data, this sequence of events is the whole story. And the reason for that all comes down to a core idea called autocorrelation.
Okay, autocorrelation. It sounds like a super technical term, but it's just a fancy way of saying something we all get. Just think about the weather, right? If it's sunny and 80 degrees today, you're not really expecting a blizzard tomorrow. Odds are it's going to be pretty sunny and warm again. The weather today is connected to or correlated with the weather yesterday. And that, right there, is autocorrelation. It means time series data has a memory. Okay, hold on. Why is that distinction so important? I mean, in a practical sense, what does it really mean that these points are a chain of events and not just a bunch of random data? That's a great question because it gets to the heart of it. It means the core assumption of most standard statistics, that your data points are all independent from each other, is totally, completely wrong here. If you treat today's stock price as just another number and you ignore yesterday's price, your model is flying blind. It can't see momentum, it can't spot trends, it has no idea about weekly or monthly cycles. You're not just missing a bit of context, you're basically ignoring the fundamental physics of the problem you're trying to solve.
And that built-in memory we were just talking about, well, that leads us straight to our next big challenge. A really powerful machine learning model, something like a gradient boosting algorithm, has zero built-in concept of time. It doesn't know that Tuesday comes after Monday or that a week has 7 days. It just sees numbers. So we have to do this kind of magic trick called feature engineering to translate the abstract idea of time into a mathematical language the model can actually understand.
Probably the most direct way we give a model that memory is with something called lag features. We literally just create a new column in our data that has the value from the day before or the week before. A lag of t-1, so yesterday's value, tells the model all about immediate momentum. And a seasonal lag, like t-7, teaches it about weekly patterns.
Can you give me a real-world example of that seasonal lag? Why does that matter so much?
Oh, for sure. Think about forecasting how many people will walk into a coffee shop. The foot traffic on a Saturday is probably an amazing predictor of the foot traffic for the next Saturday, way more than the traffic from Friday, right? That t-7 lag feature is explicitly telling the model, hey, to figure out this Saturday, go look at what happened exactly 1 week ago. It's directly encoding that weekly rhythm, that weekend rush, right into the data for the model to see.
So building on that, instead of just looking at single points in the past, we can summarize recent history using what are called window features. A rolling mean, for example, averages the last 7 days of sales. You can just picture a little 7-day window sliding along your data, calculating the average as it goes. This smooths out all the daily noise and helps the model see the immediate local trend. A rolling standard deviation does the same thing, but it captures how volatile things have been lately.
So how is a 30-day rolling mean any different from just taking the average of all the sales data you've ever had?
That's a fantastic question because it highlights a supercritical choice. An all-time average, what this table calls an expanding mean, treats data from 5 years ago as being just as important as data from last week. A rolling mean, though, has a fixed window. As it slides forward in time, the oldest data just drops out. This makes the model way more adaptive, way more responsive to recent changes in behavior, which is usually what we care about the most. It's all about prioritizing the new normal over ancient history.
Now, here's a classic trap people fall into with feature engineering. Let's say we want to encode the hour of the day. If we just number them, 0 through 23, the model sees this massive numerical jump between 11 p.m., which is hour 23, and midnight, which is hour 0. To the algorithm, the numbers 23 and 0 are just super far apart. It thinks these two moments in time are complete opposites, when in reality, they're right next to each other. This little glitch can completely destroy a model's ability to learn daily patterns.
And the solution to this is actually really elegant. We use a little bit of high school trigonometry, specifically sine and cosine, to map those hours onto a circle. Just think of a 24-hour analog clock. On that clock face, hour 23 is sitting right next to hour 0. By encoding the time into two new features, a sine component and a cosine component, we're basically telling the model the exact XY position on that clock face. And just like that, the transition from 11 p.m. to midnight is perfectly smooth and continuous, just like it is in the real world.
Okay, so we've been super careful, we've engineered our features, we've taught our model about momentum, trends, seasons, and all those cycles. Now we have to pick the actual engine that's going to power our forecasts. And this is definitely not a one-size-fits-all deal. Different models have totally different philosophies about how to tackle the problem.
So on one hand, you've got these classical statistical models like ARIMA. Think of a stable manufacturing process, the data is clean, the patterns are really clear, and you want a rigorous statistical model. That's where ARIMA shines. Then you've got decomposition models, like Meta's Profit. Let's say you're a retail company. You've got strong weekly and yearly patterns, a ton of holidays that mess everything up, maybe some missing data. Profit is built right out of the box for exactly that kind of messy business data. And finally, you have modern workhorses like gradient boosting. Imagine forecasting demand on an energy grid. You have past demand, sure, but you also have weather forecast, economic data, event schedules. Gradient boosting is amazing at combining all those different inputs to find really complex, non-obvious patterns.
That gradient boosting model sounds incredibly powerful, but the table calls it a black box. What's the actual trade-off here between something simple and easy to understand like ARIMA and a complex black box that might just be more accurate?
That right there is the central tension in modern machine learning. An ARIMA model is beautifully interpretable. You can look at its parameters and say, aha, the forecast is going up because of this strong positive trend we found. With gradient boosting, it might give you a jaw-droppingly accurate forecast, but trying to understand why it made that prediction is next to impossible.
And this quote from the source material just nails it. With a model like LightGBM or XGBoost, the reasoning is spread out across hundreds or even thousands of tiny little decision trees. It works, and often it works incredibly well. But if a stakeholder asks you why the sales forecast suddenly dropped by 20%, your only honest answer might be, well, because the 1,000-tree model said so. And for high-stakes decisions, that can be a really uncomfortable spot to be in.
Okay, this brings us to the most critical part of the entire blueprint. I mean, this is the part drawn in red ink with warning signs all over it. If feature engineering is the alchemy, then avoiding data leakage is the sacred, unbreakable vow. It is the single easiest and most common way to create a forecast that looks amazing on paper, but is completely, catastrophically useless in reality. It is, without a doubt, the cardinal sin of forecasting.
To really understand leakage, just ask yourself this question. What if, during its big training exam, your model got a little peek at the answer key? Well, that's exactly what data leakage is. It's when information from the future, the very thing you're trying to predict, accidentally sneaks into your training process. And that gives your model this totally unfair advantage, a problem we call look-ahead bias. And here's where the disaster usually happens. K-fold cross-validation is a gold standard, trusted technique in general machine learning. But for time series, it is fundamentally catastrophically broken. See, it works by randomly shuffling your data into different buckets for training and testing. But when you shuffle time, you destroy its very essence. You end up training on data from June to try and predict what happened back in January. Wait, are you serious? You mean a standard textbook technique just completely breaks here? Completely, 100%. It's like letting a student study the final exam before they even take the midterm. The model isn't learning to forecast anything. It's learning to recognize patterns from the future that it has already seen. Your test scores will look unbelievable, like you've solved it. But the model has learned nothing about predicting the unknown. It's only learned how to cheat.
So the crucial point is this. We have to use a validation method that respects the arrow of time. It's called walk-forward validation.
Here's how it works. You train on an initial chunk of history, say the first year of data. You then test your model's predictions on the next month. Then, and this is the key part, you add that test month to your training data. You retrain the model on this bigger data set, and then you test it on the following month. You literally walk forward through time, always making sure your model's only trained on the past to predict a future it has never seen.
But the danger isn't just in how you split your data for the test. Leakage can creep in through really subtle little pre-processing steps. Things like scaling your data, filling in missing values, or even calculating those rolling features we talked about. They can all leak information if you're not extremely careful.
Can you walk me through that first one? How can just scaling the data leak information from the future?
For sure. It's a classic mistake. So let's say you use a standard scaler, which centers your data by subtracting the mean. If you calculate that mean using your entire data set, including the future test set, before you split it up, you've just given your training data a huge hint about the future. Your training data now implicitly knows the average value of the data points it's supposed to be predicting. The correct way is to calculate the mean using only the training data, and then use that same mean from the past to scale both your training set and your test set. It's a tiny detail, but it is an absolutely vital distinction.
And so, when you pull all of this together, we've reached the end of our blueprint. As you've probably figured out by now, successful forecasting isn't about finding some magical secret algorithm. It's all about process. It's about having a foundational discipline and a meticulous respect for the rules of time at every single step of the way.
So, let's recap the key principles from our architect's blueprint. First, time only flows one way. Your entire process, especially your validation, has to honor that. Second, feature engineering is how you give your model memory and context. It's how you translate time into a language a machine can speak. Third, choosing a model is always a conscious trade-off between raw predictive power and your ability to explain its decisions. And finally, and most critically, your validation has to be perfect. A leaky model isn't a forecast. It's a fantasy that will completely evaporate the second it faces the real world.
So I want to leave you with one final question to think about. When a forecast inevitably goes wrong, our first instinct is usually to blame the algorithm, right? We say ARIMA failed or the boosting model isn't working. But based on everything we just talked about, is the model really the one at fault? Or is it the architect who designed a leaky process, chose the wrong features, or just failed to respect the fundamental rule of time? The power to build a better, more honest forecast, it's in your hands. So go out there and be the architect of a more predictable future.